point of the lecture is that well, these games are fun, especially when you talk about image, what they are, what images they contain. Previously, in my lectures, I used to ask which all these images are real or fake, you know, the classical GAN slides that you'll see everywhere, right? So as you would guess that there are some images which are real and which are fake and you are not sure about and so on and so forth, right? That how good GANs are these days to be able to generate images. So red check means it's real and cross means fake. You can make your guesses. I'll not ask you to raise hands, but I'll reveal the answer. These are, the cross ones are fake images and these are real images, the check ones. They look really, really similar. Unless I tell you they actually are easy to detect. If you look closely, well, until like 2 years back, this used to be the case that you can look on the very left here that when you generate images using only the faces, the backgrounds are not so good. And then hair is quite difficult. The backgrounds are surreal, and then symmetry is not well maintained, and teeth is not really, really nice. Hair is messy, and then sometimes a gender stereotype, non-gender stereotypes are also generated. These kind of problems, if you pay close attention, if you go back to previous images and you start looking closely, you can train yourself to be able to detect whether it's real, fake, or the fake face, real face or fake face. But that was the case. So in that case, if you look into these images, so how many of you think that there are, let's say, 20% of fake images? Anybody wants to raise a hand? At least 20% of fake images. Okay, how many of you think that there is at least 20% of real images? They're all fake images. Wow. So this, how realistic images GANs can generate, that too, it was like 2 years back, 2019. Now, times have changed. Okay, I'm blocking us here. Here, these images, again, real and fake, not of the faces. And I have an agenda to present you these images, not because they are super realistic. And still, I'm going to ask the same question over and over again, maybe until the end of the lecture. Well, so how many of you think that the first image is actually a fake image? Okay, it's a patch of an image. You take some random image, take a tiny patch, right? And how many, let's say, how many of you think the last image is fake image? 7th image. Okay, how many of you think image 3 is real image? It's the image patch basically, right? Okay, so basically the whole point is that it's very difficult to know which one is real, which one is fake. And the first and last are actually real image patches. And then in between are fake ones. Surprisingly though, the network has never seen any real image. So previous images I showed you of the faces, at least network gets to see images, right? And then learn from real images. In these ones, it doesn't see any real image. And it's still able to generate images that look like real image patches, and is able to fool at least some of you, right? So it's difficult. So the whole point is that, okay, now, why are we even doing this, right? That we're just generating images sometimes of the faces that look super realistic and then call them deepfakes. Sometimes you just create a bunch of image patches and then say, okay, now this looks like an image, this doesn't look like image. And then of course you can have a lot of discussion regarding this. But my viewpoint would align somehow in the direction of Richard Feynman, who said that what I cannot create, I do not understand. If I really want to understand what's there in the image, I should be able to generate the image. Otherwise, I just do not know what is an image, what image is. This understanding, by the way, you can read the quote that Richard Feynman's mother said after Richard Feynman was named the world's smartest man by Omni magazine. His mother said, if that's the world's smartest man, God help us. Anyway, so to be able to understand, we should be able to generate, oh, that's the premise at least, right? And then now we are going to dig a little bit into it. What do you mean? What do you even mean by generations? Of course, you see from the results point of view that I can see a bunch of images that's been generated, but what are you actually looking for? So that comes down to saying that what is understanding in the first place? So if you open the book Deep Learning, and in the very beginning, there is a very weird theorem. It's called no freelance theorem. That no matter where you go, you may be offered free lunches, but it's not really free. There is something behind actually. So understanding that nothing is free, especially lunches are not free, is understanding. So let's talk about what is the no freelance theorem, right? So no freelance theorem says that, okay, if you are asked a question that what is the best machine learning algorithm? And then answer happens to be, there is nothing like that. Best machine learning algorithm. That means you can have algorithms. You see, on the x-axis is the type of problems. Y-axis is the performance. You can have this red one means this particular problem can be solved very well using this particular specialized algorithm, right? But will not do as good elsewhere. It's saying that becoming a good engineer doesn't make you a better doctor, right? It's more about the domain-specific knowledge. Or maybe you even become worse doctor. Because on an average, learning or not learning is actually the same. Depending, if you are given all kind of problems to deal with in your life, then you will be as good as somebody who has not learned anything at all. You can see that this general purpose algorithm, if you may want to make one algorithm that is general purpose, is not good for anything. That's going to be as good as a random guess. What a measurable point to start, learning things that, first of all, it says that there is no hope of doing anything in the first place, right? But on the other hand, we know from our experience that things can be learned, right? But things can actually be learned domain specific in many sense. Actually, if you go to this philosopher, David Hume, in 18th century, he's one of the biggest names in philosophy during the Enlightenment period, that he already knew no freelance theorem, who said that even after the observation of the frequent conjunction of objects, we have no reason to draw any inference concerning any object beyond those of which we have had experience. That means whatever you have in the training data and the corresponding label, that's all you can say, and you can say nothing about your test data. And for that, we're going to have some thought experiment. What does that even mean, right? Let's say in your room, one day, you found out that there are a bunch of holes on the wall. And next day, there happen to be more holes, tiny holes. You're wondering what's happening. And the other day, there are even more holes. Now you're basically, all you have is this bunch of holes means you just have data. You have nothing more than data, right? There are a bunch of data points, and then you're trying to make a guess that what is happening here. It means you're trying to figure out some kind of patterns, or you're trying to learn something. You can say in many words. And then you're trying to understand what's happening with these data points, right? The data points in this time is coming as a form of these holes on the wall. So based on these holes on the wall, unless you do not make any assumption, you cannot say anything about where are the holes going to be, next holes going to be, right? And where are these holes coming from, basically. unless you make certain assumption that there is a neighbor on the other side who likes to play darts. He's throwing darts so hard that actually it makes hole through the wall, or your wall is very thin. So as soon as you make certain assumption about your neighbor, then you can make cases that, okay, how good your neighbor is playing dart, right? You know that he's playing dart game. Then you can say, okay, if your neighbor is hitting the dart consistently at the same place, maybe your neighbor is a good dart player, otherwise not, right? Those are the kind of cases that you can start making. Those are the part of, see, in the very beginning, you couldn't even make a guess that most likely those darts holes are going to be making more or less like a circle, because my neighbor is basically targeting on the dart board, right? But now you know that, or at least made such an assumption that your neighbor is actually playing a dart, then I can somehow say that it's going to be somewhere making circular patterns, right? And more so that you can even more of the distribution that where the, depending on the what game, I don't know how many of you are familiar with different kind of games in dart, but darts would come with different kind of rules, and different rules will, make you target to different locations depending upon which particular numbers you are at that time. And basically this high red or this high density points means that you get more points if you hit there exactly. And then the blue means you get less points, and this is 20, this is 40, and so on and so forth. So basically that's how you play the dart. So there's always some incentive for a player to hit at certain locations given the instance of the game. So you can make all these kind of assumptions about there must be some game happening behind, and all I get to observe is the data points. Now I have to make some kind of, maybe can learn something, and what you end up learning is something called the distribution of your data, right? Here I'm showing you the distribution of the data, that how the data gets distributed on your wall, within or around a circle, right behind where the board has been, placed. And that's pretty much what you can do actually, just based on the data. But that's not less. You see, now if your neighbor hits somewhere nearby here, you can safely say that neighbor was actually targeting at this location, not here, right? They just missed it out. And those kind of inferences you can make. And if you given, points in certain order, you can say, okay, this might be the game the neighbor might be playing. Of course, beforehand, you don't even know which all games exist, right? And you need to know which all game exists to decide which game the neighbor is playing. But to model how the data is going to appear, you just have to make an assumption that the neighbor is playing a game, that's all. Right? And game has this particular form and so on and so forth. And that's more about the expert knowledge, right? All right, so what we are generally interested in this regard, it's you are given a bunch of data points. You want to model some kind of distribution of the data. And that's really crucial in machine learning or in general understanding. And that's why the first day, the lecture, you learned about this distribution modeling of joint distributions of PX, PY, and so on and so forth. And you will have these marginals, and there will be X is the data, Y is the label, and these things. Actually, these are slides that I borrowed from Sandesh, who delivered the lecture on the first day. All right, so this is going to be crucial. It's going to be crucial to learn the distribution of the data so that it will allow you to make inference later on in a more meaningful way. Actually, if you have no clue about the distribution of the data, I can show you in few steps that there is no hope. So here X is one set of features. Y is this binary, L is the binary labels, 0 or 1. Let's say head or trail. H is the hypothesis that basically maps the data, so that basically generates the label, that generates the label. And then U is the uniform distribution of the hypothesis. Okay, maybe this is a bit tricky, but let's just go to the mathematics directly. Okay, this may look scary, but it's going to be super simple. All right, so as is my training data. X, not in S, it means my inference data. Okay. So any machine learning algorithm that learns from the training data and infers on the inference data or test data, such that this is same as the label of the ground truth, right? Fx is basically some hypothesis that actually is the label. So I want to make a prediction for my test data X, which has been learned from my training data S, such that the label of the X becomes same as the ground truth label, right? And then probability of doing that correctly is half, even for the binary task. It means it's just saying that if it's gonna be head or tail, if you make guesses and being that same as that of the ground truth, the probability is half, which means it's completely random. Under this particular setup, if we do not make any assumption regarding the relationship between X and S, that X and S, they come from the same distribution, there is no hope that there exists any machine learning algorithm that would do anything better than a random guess. So the proof is just 2 lines. And which is this is just a mathematical way of writing. This is very obvious actually, that all he's saying is that if you are giving training data, this X1 and P1 is basically, P1 is 0 or 1, the probability of being it head or tail, let's say, of binary class, right? For data point X1, this is the pairing is given to you, data, label, data, label, data, label, right? And then what we are saying is that, so the label being equals to 1, given all these data points, right? The labels of the data points equals to Pi has no relationship whatsoever. If they don't have any relationship, this conditional part will go away, and eventually it just becomes that probability of Fx being equals to 1. And under the uniform assumption, it's just going to be half. It's okay. Don't even go to the mathematics if you cannot follow through. This whole point is that if my test data is not going to come from the same distribution as that of training data, it's better that I just make random guesses and don't even try anything. Okay, this already tells me that if I am going to do any kind of learning, I have to make an assumption that there exists some kind of distribution, and then the training data comes from that distribution, and test data also comes from the same distribution. Now let's try to design some kind of machine learning algorithm and see what happens. Unfortunately though, that doesn't happen in practice. So I'm just making things complicated. So if you have any questions, just feel free to raise your hands and then ask me questions directly, and should be able to interrupt anytime. Okay, so you must have already classified MNIST digits, right? And also even generated MNIST digit in your one of the mini project. So if you extract the feature of these digits, then it will form some form of distribution, right? And if you just take the MNIST test data and make the inference, your accuracy is going to be 99%. Voila, the problem is solved. But if you take any digits from, let's say, street signs or number plates and so on and so forth, and pass it to the same model, the distribution of these data sources is going to be completely different. Now, if you pass these digits through the same model that's been trained to classify these digits of the MNIST, is going to perform very, very poorly. Now the question becomes, is that okay? I already have learned what numbers are. I have already learned that in the MNIST digits. Why do I have to learn on the street signs, streets number, right? I mean, it just seems like unnecessary. And but unfortunately, the previous theorem or the theory we're discussing about was that your test data has to come from the training data. Otherwise, there is no point. And in this case, it happens to be not the case. So what one can do is maybe something can be done to align these two distributions. If we manage to align these blue distributions and yellow distributions somehow by measuring the distance between the distributions and hence minimizing the distance, maybe a model that's been trained on MNIST is also going to work on this data set, which is more of real image. For that, we'll have to learn some metric that can measure the distance between two distributions. And if we can measure the distance, not only measure, but same, then the knowledge learned for the data that comes from one distribution can be transferred to the knowledge to the other. Here we take one simple example. Okay, so on the left, it's a very colorful parrot. On the middle is not so colorful. And I just want a more colorful parrot, right? So what I can do is take all the pixels. I'm not even thinking about this image as a data point. Okay? I'm just thinking as a pixels as data points, right? All the pixels of these parrots, these are the RGB, right? And just map them into RGB space and represent some kind of distributions here. This is basically just RGB of this parrot, right? And then this is also RGB of this parrot. For every single pixel, I'm just plotting it there. And then if I can somehow find a means, because we are talking about some form of algorithmic paradigm, right? Some algorithm that can actually align this to this, right? I take data points from all the pixels from one image and all the pixels from other image and somehow find kind of transformations such that this gets aligned to this one. So basically that gets transformed here. This transformation will tell me how I should be changing this particular RGB value, right? Here, this map, so that this parrot starts looking like this parrot here, which is actually a very, very poor result, but as the beginning of doing knowledge transfer on the pixel level. So we are not yet in data set level, but it's actually at the very least, this parrot is closer to the first parrot than the original parrot, right? I mean, in some color form. And that's the kind of knowledge transfer that we are willing to do. For that, you understood that having the idea about the distribution of these data points, mu1, data points mu0, and then aligning those distributions of the RGB values, right, would actually help us to transfer the color or hopefully also make the corresponding inference on the second image from the first one. And then if you see in the bottom one is basically, if you see in the data set level, these are the data points that's been mapped into the lower dimensional space. It's the whole data sets, and they also follow the similar pattern where this comes from the one distribution, something like this one, and this comes from the other distributions where the model has learned, and then you can even align these two to bring the features of this form, where the blue and then light blue and green and everything, they are aligned all together here. So The one above, I gave you the example of aligning the distribution in the pixel space, and one below is aligning the distributions of the data points in the dataset space, right? I mean, all datasets. All right. So before we proceed, I just want to give you one example of how distribution mappings are done. You know, when any library that you use to generate the random numbers, they often just give you uniform random numbers between 0 to 1, right? So what they give you is 0 to 1. The probability density of getting all the numbers is basically the same. So this is uniform. Now I'm interested to know or generate data samples which are not uniform. Let's say Gaussian. So if I give you a function that generates uniform numbers between 0 to 1, do you know how to map that so that those numbers indeed come from a Gaussian distribution? Anybody has done this assignment before? Because I just get the data sample, right? Yeah. Do you want to make a comment?
Hello. So one thing that we can do is, like, if we get a data from the uniform distribution, we can treat that it is the CDF value of that function, and we can do the inverse mapping of the CDF value to the random variable that gives us the probability.
Exactly. So that's right. So what we can do is that make the cumulative distribution function of this one. And then, because this is going to be uniform anyway, to generate between 0 to 1. And then if it happens to be so, you see, I want to get something around 0.5. I think I didn't draw it very well. Let me draw it one more time. So that. So what is important to understand is that this particular thing is going to be of slightly this form of this thing because of high values here. This will quickly go off, and this is CDF cumulative. So this is 1, this is 0. See, this is getting uniformly distributed here, but because of this non-linearity, see, around 0.5, let's say, right, it covers more here. So maybe between 0.4 to 0.6, it will cover 0.2 to 0.8. I mean, some big range, right? So what happening is that probability of occurring, although this whole thing was uniform, this has more probability to occur within this particular interval, but that gets mapped into this smaller interval. Therefore, this particular probability density probability will be captured better. So now what you're going to do, if you have to generate these Gaussian distributions, is that you randomly generate a number if it lies here, and then map it to the number instead here. So even if you generate 0.6, you are going to map it to 0.55. because probability of occurring something around 0.5 has to be more, right? So even if you generate something around 0.8, you're still going to map around 0.7. So it just pushes, the numbers themselves that's been generated towards the regions where it's more likely to occur. That's based on this normal distribution and the uniform distribution being different, right? So I hope you understood the intuitive meaning that basically what is happening is taking a big space here and squeezing into small space where it's more likely to happen, right? This big space gets squeezed into small space of because essentially what happens is that the probability of occurring these events within this whole area and this small area, well, it's not area here. So whole area will give you the probability itself. But within this interval, the integral between these two points and integral between these 2 points, they are going to be the same essentially. And that's how its whole thing is shifted. I guess you can recall now what Sandesh was teaching the other day. Unfortunately, I was here to attend. He was also talking about this integral between, because this is the density function, right? The integral between two intervals is what giving you the probability of occurring any number within that interval, because probability of occurring any true number itself, if you just pick one number on this continuous distribution, is 0 anyway. So I'm giving you this example because otherwise it looks very weird if there is no region. So that this is some kind of optimal transport or some kind of transformations. Let's say this is my training data. This is my test. So they differ in 2 different distributions, right? So then I can do the mapping of one distribution to the other distributions by using some algorithm. This is just one example of some algorithm that I can use to map one distribution to the other. And that means there do exist other algorithms that can map one distribution to the other distributions. Okay. So, but the main problem in this case is that modeling the distribution is not easy, because I gave you the example of uniform distributions just of 1D, right? But we're talking about the whole images and audios or text and so on and so forth, a very high dimension. So modeling the distribution is not easy. Aligning those distributions is not easy either. And these are the 2 problems that we will be discussing today's lecture and later, that how you model the distributions implicitly and how do you align them. And both of them you can do using adversarial training framework. Using GANs, it's not just to generate images, it's rather to represent the distributions. If you can represent the distributions, you can already say that you understood the data, right? Modeling the distribution of the data, that's what we discussed so far. And then once you model those distributions, if you can do that for different domains, and if you can find a means of aligning them, then you can also transfer the knowledge between or across domains. So, but unfortunately, 2D image is not a 2D point, just like the examples I gave you before. So that's why it's gonna be quite a lot of complexities that we're going to face. By the way, this is the image that I took in the place Bhaktapur on the night of Yomari. It's very nice. Anyway, so here we stop and ask you. I stop here and to ask questions. If you have any questions so far, please grab a mic and ask questions at the same time. I also must be looking into the ratings. Okay, no questions so far. Any question? Oh, yeah. Yes, can anybody grab the mic?
Yeah. aligning the distributions, like the numbers you told, does that simply mean that we are trying to shift from one characteristics to other characteristics domain?
Yes, the aligning the distributions means that if you could see or model the distribution, right? And then if you could measure the distance between them, right? And the distance between them, the idea is that the data points, once you start seeing the distribution, they will have the same distribution after the alignment, right? So before the alignment, they're not the same.
Yeah, in the sense, let's take the same image, and in this image, the distributions or the numbers, they just represent the characteristics of the image or not? Like the pixel values ultimately represent the like characteristics, like colors of the image.
Yes,
yeah.
Yes. So not the, on the right and the bottom, two examples I gave you, you have to also be careful, because one of the example is that you have RGB values, and then all the RGB values all together, right, form a distribution that represents one image, right? On the other hand, if you are taking MNIST images, then every image has one data point, right? And that data point, there are like 60,000 images, and those 60,000 images make one distribution. It's the distribution of the data set, right? So distribution of the data set will represent the characteristics of the data set. Similar distribution of the pixels, image pixels, will represent the characteristics of the image, right? So essentially, what generally what we're interested is to represent the distribution of the data set, so that the knowledge that you learn on one data set, right, can also be used elsewhere. But the elsewhere place, if it differs in distribution, then the knowledge cannot be used anymore. You see what I mean? No? If your test data has a different distribution than the training data, because test doesn't have to be just the test speed of some data set given to you, right? So test data could be that you have given model train on ImageNet. You take images of by yourself of any object, dogs or cats or mushrooms or whatever, right? And now you are trying to classify them. So images that you have taken going to have different distribution than the distribution of the ImageNet images, right? Therefore, the accuracy on the images that you have taken is not going to be anywhere close to the accuracy of the test data of the ImageNet itself, because they differ in distribution. Because distribution itself is a vague concept. It is an abstract concept. Does it exist? Yeah, it does not exist. It's well, in some sense it does exist, but it's more about the representation of data, the assumption that the data actually does follow certain distributions, right? And that distributions of the training data has one, and as long as the test data comes from the same distribution, there is no problem. But unfortunately, in the practice, that's not the case. The training data has some distributions, and test data may often appear from very different distributions. In those scenarios, only thing that you can do, or one of the meaningful things that you can do, is somehow try to map the test data's distributions into the training data, so that you can still use the model trained on the training data, right? Make sense? Okay. So now the question still remains is that how to represent the distributions and how to align them, right?
Yeah, I have another one. Like when we do like these types of like distributions, when we normally do like in other cases, not in adversarial or modeling, do we generally when we split out data, they do belong to same distribution, right? Like when we do supervised learning and those kinds of tasks, I just remember that we take the data from same distribution to get the same amount of accuracy and all.
Yes.
Yeah.
So often your training and test data, they come from the same distribution in certain evaluation protocol. Fine. But what happens is that when you really try to test your system in the real world settings, let's say. So what happens is, okay, think about this. ImageNet is all the images taken by human. and it has human biases. Like what? Humans often tend to hold cameras vertically. They don't go close to walls and take pictures. They don't take the pictures of the ground. They try to take pictures of something pretty and beautiful and whatnot, right? And then if it's a bad image, they throw it away. On the other hand, if you mount a camera to a robot is often taking the pictures of the walls and ceilings and grounds and all these crazy things. It's because often it takes pictures when it's too close to the wall, right? Often it takes pictures when it's not camera, it's not vertical. And it does all kind of weird things. Now, if you take a bunch of pictures taken from the robot and try to pass it through the imaginary pretend models, which are actually biased by the humans, this model is not going to do well because it has never seen any images like this. So these are the differences, right? Differences of the images is that all the images in cityscape or many data sets are taken in during the day. And if I take my camera, I go in the night, I have very different lighting conditions. I might have ended up in a completely different city. Things change completely differently. And that's also the case for us actually, right? Because when we learn certain languages, we just learn that particular language and we don't understand the other languages because we have not learned yet. And so do the machine learning algorithm. They also suffer the same problem that whatever they have learned, whatever data they have exposed to, will learn from. But some good things about us is that we can quickly adapt into the new settings, new languages, new environments with only a few examples and sometimes even without the examples. But these machines, they cannot do it that easily. And these gaps often occur because of the constraints in the real world and the changing environment and then different acquisition devices and so on and so forth. And therefore these distribution differences are bound to happen. And unfortunately though is that you cannot really have one model that works across all the distributions. And then, but there is a hope that you can take a model that works on one distributions and decently work well on the other distributions too, even if it hasn't been trained yet. And that somehow can be done using the adversarial training. All right, so that was the motivation of doing GANs. And now we start, how do you do GANs in the first place? So in some sense, generative networks are opposite of, let's say, classifying or understanding networks. So the discriminative networks or discriminative models actually take the data and then try to understand to predict the labels by predicting labels. Whereas generative ones are the opposite. They take the labels and then try to predict the data. Of course, it's going to be ambiguous that there is not only one cat for cat, there are many cats, right? Therefore, I should be able to, when it's been asked to generate a cat, I should be able to generate varieties of cats based on their likelihoods. And hence my generator needs to model the distribution of the data somehow. And that's how the GANs, so that's what the GAN's supposed to do. So this particular slide you might have seen in many places. It's a two-player game. There is a generator that generates a fake image. See. So previously I told you that it's going to take a label, but you may not even have a label. So if you do not have a label, what do you do is you make up a label. A label doesn't even have to be discrete like cats and dogs. It's just some random vector. And this is the label in that sense. In that sense, this is basically the label, some continuous labels. that comes from the Gaussian distributions. And then that's been fed to the generator to generate some image that we want it to look like a cat. This fake image goes to a discriminator, which is basically a classifier and nothing else, that learns to classify if the image comes from the generator or real data. You have got real data given to you that you want to learn from. And this discriminator will learn to classify if it is real or fake. It will say real or one if it comes from real data distribution. If it says fake, if it comes from the generator. And since this is just a binary classification problem, you can use a binary cross entropy. Right? So the way you can think is that you forget about this thing for the time being. Assume there is no generator, but somehow there is a fake image. And just train a discriminator that does nothing more than binary classification. You have already done some classification examples, right? Image classification into MNIST classes. So if you are given a bunch of real images, bunch of fake images, you just have to train a classifier that just classifies is real or fake. Once that's been trained, so discriminator has been trained. So now what you want to do is you forget about discriminator, you forget about this, and go here. So you just do one at a time, okay? It's just a bi-level optimization. You don't think it once. You just think one after the other. So you go here, and now you say, okay, you ask generator, generate some image, you don't care much, such that this gets classified as real. You're training a generator to generate something when this fed into the discriminator gets classified as real, and hence it starts looking more and more realistic. But then you go back again and say, okay, I'm done with training the generator. I go to discriminator and then train discriminator saying that, okay, now this has been improved, right? This fake image has been improved. Now learn that this is actually still fake, this is still real, and classify using binary cross entropy again. So you just do back and forth training between these two, on and on and on. So doing this back and forth training of discriminator and generator is what called adversarial training. So one gets trained to fool the other. Generator gets trained to fool the discriminator, but not what the fool. Discriminator is trained to catch the discriminator. It's like one is fooling and one is trying to catch. And that's the game of the adversary that takes place. So you often will see this kind of mean max between discriminator and generator. So since you will see this equation very often, and some of you might not have seen it before, and I don't want you to be scared because this equation is supposed to be simple. That what is happening here is that here discriminator is trying to find the discriminator that maximizes whatever this loss term, right? And find the generator that minimizes the whole thing. So first, this thing is done. So you find the discriminator that maximizes, right? So maximizes scores means says that, okay. So basically in the binary cross entropy, the minus log is taken, right? This is minimized. Basically, if you don't put the negative, this term is maximized. So, right? And you train your generator such that when it passes through the discriminator, the generator takes the noise, pass to the discriminator, right? This discriminator will tell me things are close to 1. This is real. So and hence the whole thing gets minimized. So this is, you can just think as the cross entropy loss, and the trick is that discriminator generator basically generates the image. This is the generated image that goes through the discriminator so that the generated image gets classified as real. And that's where this mean max games takes into place. This is just the mathematical way of saying what I told you before about one gets trained to fool the others and other gets trained to catch the generator. And in your source code, it's not that difficult to know. Basically, you can just parse your code into two parts and you should be able to see quite easily those things. Okay, whole point is don't be scared of these equations. So this is the code by Jan LeCun. You might know him already, CNN and then Turing Award winner. And he says that, said a few years back that generative adversarial networks is the most interesting idea in the last 10 years of machine learning. He said that a few years back, but still that's valid. It's so simple and it can really do many things. And that's not mostly because it can generate images, it's mostly because it can model the distribution and somehow align them. And this, why am I here already? Idea of the general idea of learning by competition between players, it backs very, very back that things are learned by competitions. Things are difficult because you can grow up, you can learn more from the difficulties, right? And then you become better and you face bigger challenges. I don't know if I can actually share the audio. Can I share the? Can I share the? Yeah. I didn't share this thing in the first place with the audience. Okay, maybe. This is 4 minutes long video on adversary. Anyway, so maybe I can just voice over. Sorry? Okay, sorry to those. Yeah, sorry to those who are in Zoom that were disconnected. Audio was disconnected for a while. So basically, we are playing a video that was demonstrating the Nash equilibrium of two players game, two players zero-sum game exactly, and then shows in the video that how the game takes place in the more social circumstances, and that mathematically resembles to the adversarial training of our generator and discriminator, where one tries to do better than the other. So in the min-max game, and there exists a theorem, and then John von Neumann has famously said that as far as I can see, there could be no theory of games without that theorem. I thought there was nothing worth publishing until the min-max theorem was proved. So this happens to be a very, very crucial idea, that adversary way of modeling, learning, seeing the world is very crucial. And fortunately, at least in some circumstances, the Nash equilibrium or the equilibrium of that system does exist. And fortunately for us, training generative adversarial networks does lie in that case. Therefore, don't listen to people who talk about mode collapse all the time. Well, there are other problems, but not the problem of not existing of the Nash equilibrium. So this is just one more example. I'll go very quickly, because this is the kind of example settings you will see in game theory. That there are two players. One is a blue player, one is red player. Blue player has to make choices between A, B, and C. Red player has to make choice between 1 and 2. I'm more or less just trying to help you to read the table, not much more than that maybe. So for the red player, choosing the yellow box is clearly the better choice. If the blue player chooses A, and red player can safely choose 1, and hence red player can get 30 points of whatever benefit. Similarly, for blue player, if red player chooses 2, choosing C is the best choice. So the question is that no matter whether you try to, whether you try to minimize your damage or maximize your benefits, you end up to the same outcome. That's the beauty of the min-max theorem on these particular settings. That here that in this particular scenario, that A is losing 30, because zero-sum means one loses and other gains, like playing football or many kind of competitive sports, right? That for one to win, other has to lose. And not all the games are like that, but the game of the adversary, the game of the adversarial neural networks is of that kind. Here, that's why this is a zero-sum game here. And everywhere you can see there's a zero-sum, that whatever one loses, the other will gain. And then let's say that the player, randomly they start from here. So if they're in this particular setting, then it's clear that the red player will make a move to go from here to here, so that red player can have 20 points gained and the blue player will lose 20 points, right? And then if they end up in this particular setting, and it's obvious that the blue player will rather make a choice B, because red player has made choice 1. And so that B player can have the 10 points gain, whereas blue player will have 10 points gain, whereas red player will have loss of 10 points, which is not the ideal case scenario for the red player. Therefore, the red player will make a move again, and so on and so forth. So the game continues that way. The question is that, so in certain scenarios that the equilibrium will exist, just like the video that we saw before, that they stop making choices or moving. certain cases they do not, and certain cases they exist some kind of the dynamics. They go into the loop and the same loop repeats over and over again. Anyway, so in our case, the Nash equilibrium does exist. Therefore, it's safe to have the generative adversarial networks train on one after the other. And this particular expression is just to show that on the left, if you are trying to maximize the damage or minimize the gain, so if that's not again true. So this if y is trying to minimize and then x tries to maximize, right? So that's because one minimizing the function would incur to the maximizing to the other. So because they are two different players. So that would be same as doing the opposite of doing the min max. So min max and max min in these particular settings happens to be the same. Eventually the outcome turns out to be the same, and that's the theorem can be proven. I guess that's more interesting from the game theory point of view, but all I wanted to give you was a slight test of how the generative adversarial networks are connected to the game theory, and how the adversary comes all together, and how powerful the way of seeing the adversarial way of learning, to learn the data distributions, to learn the data distribution alignment is going to be. So this is one of the most famous paper in GANs. The most famous paper in GAN is Generative Adversarial Nets by Goodfellow et al. And if you go to section 4, this exactly the paper says that generator Z implicitly defines a probability distribution PZ, right, as the distribution of the samples GZ obtained when Z comes from PZ. Right? So basically, generator is indeed trying to model the distribution of the data. Coming to the adversary, so in the learning, in the vision, in the AI community, it is also believed that just like the animals have evolved based on the natural selection, the intelligence had grown based on the adversary between the mobile agents. So what happens is that in the beginning, when animals could see each other, there would be prey and the predator, and then the prey would try to run away from the predator. But it's not only physically, right? They also have to see better. They also have to understand better. They also have to predict better. This kind of adversary between prey and predator in real world evolutionary setup has eventually gave the rise to the intelligent self. And if we can bring that evolutionary benefit or the evolutionary paradigm of intelligence into the framework of machine learning, that would be great. And that's what these generative networks do offer to us. So adversary is really more than opponent, rival, enemy. It's really much more than that. So in this sense, that here you can see that how the adversarial game is done is that if in the front you have to agree with your opponent, right? But at the back you always have a mind that you are going to do otherwise, just like the discriminant generator. But eventually they have to agree because there is nothing better to do. You cannot do anything better than that, and that's the Nash equilibrium that you want to reach. That's what the adversary is. Adversary is just not just only about the opponent. Okay, so I can take a question here if you have any question before we proceed to how the adversary actually helps us to training, even before we actually go to the GAN framework. Can you grab a mic?
Hello. So I was just wondering how common it is for models to reach this point of equilibrium, and how, like, is it realistic for big enough models to have enough resources in the current climate, current setting, like, to reach this equilibrium easily? Or
well, things do work, right? GANs work. That's what you're talking about. In that sense, from the outcome point of view, yes, they do. But then question is, do they actually reach the Nash equilibrium or not? And you can never be sure about it. It's just that you have a hope that there is a chance of reaching the perfect Nash equilibrium. Is that actually achieved? Well, maybe that's not really necessary. That's actually goes something similar to, you can hold the mic. We can. So something similar to this, right? That you can train your neural networks and achieve good enough models, although locals are actually good, right? It does also have the globally optimal solutions, may or may not be attained. Similarly, here also, that is, the stochastic framework will give you good enough solution. And not only that, the theoretical framework will offer you that there exists a almost perfect solution that you're looking for. Therefore, there is nothing to worry about. Of course, because of the practical limitations, that may not happen, but they do give you good enough solutions. And that's where we often, in the stochastic framework, that's what we often are happy with. And they generally, from the engineering or pragmatic point of view, they actually do work, especially with the modern advancement in GANs, they actually work quite well. It's just that if you want to learn from small amount of data, which often happens the case in practical scenarios, or if you want to learn from noisy data, there are many other problems, right? More than the theoretical sides. There, it doesn't seem to be work that great, and that still remains to be research topic rather. Yeah. Any more question? All right, so let's take an example of class domain gap or distribution learning here. So I believe that you have seen this particular diagram before, where you have a bunch of images of objects, which we call source data with labels. You can train that using an encoder and classifier using the classification laws, right? So that's the source data that's been trained. Now what you're interested, use the same model. You see, these bags on the top, the bag and the chair and everything on the top looks quite different than the bag at the bottom. And then if you pass those images through the encoder, so, and you get the features, if you pass to the same classifier, the performance is going to be bad because of the gap in distribution. What you can instead do, since you don't have the labels on the target data, you can put a discriminator, and now the encoder will offer you one set of features for the source data, other set of features for the target data, right? So what we are interested now, say, maybe this is not really the perfect example, but this is like one of the distributions and the other of the distribution, right? So this comes from the source, and this comes from the target. And then first what you can do is, this is just a classifier that says, okay, this will say whether it comes from the source and the target. And then this encoder will try to fool this discriminator. So only way this encoder can fool this discriminator is by generating features for both source and target, so that the distribution of the source and target, they look the same. When the distribution of the sample, distribution of the source and the target samples look the same, then this discriminator cannot say where it comes from. And that's what happens to be the Nash equilibrium, that you're confused. You cannot say where it comes from, right? So that way the distribution get aligned, And hence, since the distribution get aligned, you can use these encoder with this classifier to perform the classification. So since discriminator is a classifier, in one stage of the training, it can say whether it comes from the source or the target, right? But because of the adversarial learning, this encoder is also trying to fool the discriminator, and hence it will automatically end up generating the features from the target data with the distribution same as that of the source data. So now this distribution and this distribution, they end up being the same or similar, and hence you can use this target data without the labels using the same encoder to the classifier and perform the classification much better than without having the adversarial loss. So let me iterate this here more up from the problem setup point of view, that you have got one data source with the labels, you have got another data source without the labels, and you want to learn a classifier on the data source with the labels and use that classifier with the data source without the labels. The premise is that the target data has a different distribution as that of the source. We discussed about why does that happen. If it is going to have the different distributions, encoder feature will have different distributions, but then we can align these two features distributions by training a discriminator together, which will have the adversarial loss. And hence the features of the target data as well as and the features of the source data will have the same distributions. That's the only one you cannot say where it comes from, right? Think about that. You have any two players playing the dart again, and if they are hitting at two different locations, you can say this is the one player hitting the darts and this is the other player hitting the darts, right? But then when they are hitting everything all together, then they are so well merged, right? They look the same distributions. You cannot even say that where these data points comes from. And that can be done, the distribution alignment can be done by means of the adversarial training, where simple thing that first you try to classify where it comes from, and the next you try to generate the features to be classified by the class classifier such that the discriminator cannot distinguish. That's a very simple, neat, clean, and one of the best way of aligning the distribution. It's called the optimal transport. Yeah, please. Yeah.
Hello. Yeah. In the previous slide, like we have an image data set and we are passing through the encoder network. And you are saying that we are aligning the distribution, but the encoder network is really generating the data distribution or just is encoding the image into some low dimensional vector space?
It is, okay, we can say data points at any point of time, as long as the features are represented to the image. I can arguably call it the data distribution, but let's just go to the feature distribution. So it is generating features suitable to classify by a linear classifier. That's where you pull your features, right? So before this classifier is basically linear classifier. Now you're using the same encoder to extract the features for the target data, right? And you are assuming or hoping that the target data will also have the same distribution as that of the source data, which unfortunately doesn't happen to the case. And that can be aligned without requiring the labels of the target data by means of the adversarial training, where the adversary is taken place is done first by classifying where the data comes from and then training the encoder, right? So that the discriminator cannot say, or basically fooling the discriminator while you are training. And that eventually makes sure that distributions of the source data as well as the target data's features going to be aligned. Does that make sense?
So here, like, so at one step, we are just training the discriminator part, and at another time, we are just training the encoder.
Yes. So basically, you still the adversarial framework. 2 trainings take place. Once you train your discriminator, everything is fixed. And then the second time you fix your discriminator and everything else gets trained.
So is that setup is different from when you train this whole network in an end-to-end fashion, like simultaneously? Simultaneously, what you can also do is like we can have a same encoder network where they're setting the parameter, and we are calculating the loss in the classifier layer also, and in the discriminator, like it also classifier layer. And when you do combination of loss and like train in that setup, will it be anything different?
No, you cannot really train the discriminator together with the encoder. Well, that some technique can be done, but not in the adversarial fashion, right? So now we are in the adversarial fashion. So adversarial fashion will actually separate out 2 agents, let's say. There are always 2 agents in adversarial setups, right? Here, one agent is the discriminator and one agent the rest of the things. So what you do is you first train rest of the things as is, doesn't really matter. And once that's finished training, you only train the other agent, which is the discriminator, to classify where the features come from, because the initiations, they come from different distribution. That's why it's going to be easy to classify, right? So then you finish classifying your discriminator, then you fix it, and you now train your encoder such that it will have 2 losses when you are training the encoder, both the classification loss of the class classification as well as the adversarial loss, basically the negative of the classification loss of source or target of the discriminator, right? So that's and then you just alternate between these 2 over and over again. So that's how the adversary comes into picture. So in some sense, you can even think that the encoder is just generating features to classify, right? The whole encoder is just generating features to classify, and discriminator is still a discriminator, just like in the GAN setting. But then it is actually, it's been condition open, the source and then target data, irrespective of it's been condition open, it has to generate the same distribution, because otherwise the discriminator, it will be easy for discriminator to figure it out, right? And the Nash equivalent will reach exactly at the point where the distribution of the source data and distribution of the target data would align perfectly. That becomes the most difficult for discriminator to figure it out, right? And that's what the generator would also want to do. It generator now is this encoder in that sense. Yeah. Anything else? Go ahead.
So can we say that? Yes. So can we say that it is aligning the encoder features distribution instead of data distribution?
Yeah, more accurately, yes. More accurately, we should be saying that is aligning the feature distributions of the data. Yeah. Anything else? Let's see what slides do I have. Anyway, so then actually we did some theoretical analysis about things, or at least a discussion about theoretical things. So it happens that if you do not have any prior knowledge about the target data, and if you still believe that the target is not too far from the source, because at least to us is not, right? Because we can still make inference, then the only way that you can do is the optimal transfer, do the minimal adjustment necessary, right? To align the distributions. And then distribution alignment in that particular premise happens to be the best thing to do. And theoretically, one can show that in the very same setup, adversarial training is the optimal thing. There is nothing better than doing adversarial training. It's a difficult thing. Okay, we're talking in 2 different regards. One is about, okay, it may be difficult, but that's the best thing. If you can get the perfect solution for your adversarial training, that's the right solution you're going to get under these settings. Therefore, this is one of the paper that says, what's one of the quite famous paper on domain adaptation that says that, we have got some questions here. What does that mean? Okay, so Kiran, the adversarial loss will will increase and be at the plateau, just like in the GAN settings, that it will not keep on increasing. But yeah, in the very beginning, it will be easy to classify. Therefore, adversarial loss will be low. And then later on, it will be difficult to classify. So ideally, you want to have the loss corresponding to 50-50 classification error, because you cannot say whether it comes from the source or it comes from the target. Therefore, your accuracy of the classification should be 50%. Yeah. So then this particular paper says that the representative functions should be designed to minimize the domain divergence, basically the distribution distance between, in some sense, because I guess you also study about KL divergence, JS divergence. They're also comparing distributions, and those distributions comparisons of distance or previously we discussed that need to be minimized, as well as the classification error, of course. And then in the previous settings, that so discriminator minimizes the distribution distance, and classifier minimizes the classification error. And that's basically what this particular paper is saying. If you want more mathematical details, you can follow through the paper, but the whole idea is the error of the hypothesis is bounded by the distance between the distributions of the source and the target. That closer the distributions, less the error that you're going to have. And if the data come from completely different distributions, of course, you're going to have more errors. And you can read more papers on that line. I guess, what's the time now? Okay. I guess we can stop here. We will be discussing more about the GANs themselves, because I know you like GAN, everybody likes GAN, and let's see how the defects are generated. So defects are generated by using conditional GANs that we'll be learning on day after tomorrow. The lectures I said that got cancelled and will be replaced. That will be more regarding the conditional GANs, and already we'll talk more about domain question, semi-supervised learning, and then we'll also do some unsupervised learning at that time with 3 hours. So for now, we can stop here. If you have any question, you can ask me now during the coffee break anytime. Thank you. Any question?